Okay, here's a example from 9.3, which is about significance testing or hypothesis testing. We want to test a claim. This one's about a mean. So we have a classic rock radio station. They're claiming to play an average of 50 minutes. However, it seems that every time you turn to the station, there's a commercial playing. So you want to investigate the claim. We always do that by selecting a random sample, get some data. So you select 12 different hours during the week and record what the radio station plays. And there's your data, there's your list there. That is the number of minutes of music in each hour. And again, the station's claiming that they average 50 minutes. Okay, so let's see if we can test this claim and kind of make a decision. So in order to test a claim, we need to verify some conditions, make sure everything's met here. So we have 3 conditions to check. We need to see if we have a normal spread going here. So for a claim about a mean, we can either have a population given as normal. Did they tell us that? I don't believe they did. So that one we don't know yet. The other option with means, remember the central limits theorem says that the sample size is large enough, then it doesn't matter what the population is. And in our case, our sample size is only 12, so that's not met either. So our only other option is to plot our sample data and see if it looks approximately normal. So that's what we're going to have to go with. And remember, the best way to do this is to use the normal probability plot in the calculator. So let's go ahead and enter the data into list 1 and look at that normal probability plot. Okay, so I actually already went in and I entered the data, so we got all 12 values in list 1 here, and we're going to go ahead and use the calculator to come up with that normal probability plot. And again, what we're looking for is some sort of linear pattern that will tell us the data is normal. And again, it's a linear pattern in the normal probability plot. It's not that the data itself is linear, because we don't even have x and y values. We just have one list of data. But in the stat plots here, that last option for type is highlighted. This is going to plot our data against what its z-score is. And if that shows some linearity, then we'll be pretty safe to assume the data is normal. So everything's set up right on the plots. I'm going to go zoom stat. Zoom 9, a little trick to get the best viewing window, and we can kind of see a pretty linear pattern going on. There's definitely some linearity there, 1 or 2 points a little bit below or whatnot, but that's not too big of a deal. Remember, we're just looking for something that's obviously not linear. If we saw like an exponential growth shape here, or a parabola or something crazy, then we would probably have to not go with the normal condition. We'd have to not be able to do this problem actually in this class. But so we look good. So make sure when you're doing these problems, you state something about that, about a linear pattern in the normal probability plot. So normal, I'm going to abbreviate here. Normal probability plot was linear. Okay, and it may even be best just to give a quick sketch, especially on an AP test or something when they're real picky on these conditions. So we got normalness, random. That one was given to us, so they told us it was a random sample. And then the independent condition, let's see here, independent deals with do we have a large enough population size, and in our case our sample size of 12, this was talking about a given week, I believe. Yeah, it was all about in a week, so there are more than 12 times 10 hours in a week. So the population size n is greater than or equal to 10 times lowercase n. Again, this is the number of hours in a week. That's the population here. And I believe there are more than 120 hours in a week. Okay, so just mention something about that. That makes sure that the independence works, that the standard deviation is going to be what we think it should be. Okay, so we got our conditions are met. So we're able to use our process. So let's go and set up the statements. So let's write the hypothesis statements here. So the statements, okay, again, the whole thought process here is that we're going to assume that their claim is correct. Okay, the null hypothesis, we're going to assume that the mean really is 50 minutes. Okay, the null always has to include an equal sign because we're going to assume it's true, and we're going to use that as the mean or as the center of our distribution, of our normal curve or t-curve. So it has to include the equal sign. It's the alternative hypothesis that'll have the greater than or the less than or the not equal. And in this case, we think it's less than 50 minutes. Okay, we're getting a commercial every time. Doesn't seem right. Okay, so we need to then just make a little statement for the reader of your problem that mu is the number of minutes, or number of, yeah, let's say minutes of music each hour. Okay, that's defining your parameter. What is mu? Okay, so that's what mu is, number of minutes. So now we'll go ahead and do our calculations. Okay, with the sketch here, of course. And we need to ask ourselves, are we using a z-curve or a t-curve? And is it a normal z or a t? In this case, we do not know the population standard deviation. Okay, it was never given to us. We do have some data though, and we know the standard deviation of it, or we will get that from the calculator. So we're going to be using a t-curve. And let's get those values right now. Again, the data is already in list 1. So let's get the one variable stats of that. There's our sample mean. We'll go 47.92. Standard deviation, we're going to use the SX. Okay, that's going to be our standard deviation of our sample. And then our mean, of course, X bar. We're not going to use this. I know there's, it's tempting to say, isn't that the standard deviation of the population? And it's an estimate of that. Okay, it's using our sample to estimate what sigma really would be. But if we don't know all of the values, we don't know for sure what sigma is. So don't think that since the calculator gives you that, we can use z and a normal curve. We don't know the population standard deviation. We just have a sample of data. Okay, we're going to use S sub x, and we're going to have to use the t-curve for that. So let's go 2.81 for that, and then 47.92. So let me jot those down. X bar, it's on the side here, 47.92. S sub x, again, was 2.81. Okay, so let's use those. Okay, we're going to use the t, we're going to do the t test. Okay, so what we want to do is get the test statistic. Okay, we want to try and start figuring out this p-value. So again, start thinking about what all these terms mean. We're going to assume that the mean is 50. Okay, then we got this curve here. Again, it's not normal. It's actually a t-curve. It has the same shape, just a little more area in the tail. So we draw it just like a normal curve. Okay, so 50 is assumed to be what the mean was. That's what they told us. So we're going to believe them and see if we can prove them wrong. Our sample value was less than that. It was 47.92. Okay, somewhere over there. And again, I don't know how far out yet. We got to figure this out. Okay. In order to get the p-value, okay, the p-value is going to be the area that is as extreme or more than your sample value. What that means is it's farther away from the mean. It's going to be the area of one of the tails. Okay, some problems it might be the area in both tails. It might be a two-tailed test. If the alternative hypothesis was a not equal, then we would have to include some area up here as well. And we would basically be doubling the p-value we get in the first case. That's not happening in our problem. Okay, so let me get rid of that. So let's see, how can I do some erasing here? Let me just erase it. I'm not at the keyboard at the moment, so this is not going to be used in ours. Okay, so let's figure out what is our p-value. Okay, we know we need to, it's going to be a CDF problem. It's going to be a t-CDF problem. The lower bound is negative 9999. The upper bound is technically this 47.92. But in order to do this, we have to standardize it. It's just the way on your calculators the t-CDF works. You have to standardize and get what's called the test statistic. Okay, which is like basically finding the z-score. Okay, so what we're going to do, the test statistic, it's going to tell us how many standard deviations we are away from the mean. Okay, so the formula is always the value, okay, from the sample basically, minus what we claimed the mean was, over the standard deviation of the statistic. Okay, sometimes you'll see this denominator, the standard deviation of the test statistic, or of the statistic, is it's called standard error. Okay, and we know the formula for that. Okay, so let's find that. For our problem, our value, our sample value was 47.92. Okay, we got a minus 50 for the mean. The standard deviation, our sample was 2.81. That gets divided by root n. Okay, that's for the sampling distribution. Okay, so let's calculate that out real quick. If we do the 47.92 minus 50, and I'm going to divide that by 2.81 over root 12. So the numerator is negative 2.08. When we divide, I got us a value of negative 2.564. Okay, so that is how many standard deviations we are actually below the mean. Okay, that's the test statistic for this value right here is negative 2.564. Okay, so we were like 1 standard deviation, 2 standard deviations, another standard deviation. This would be 3. We were about 2.5 standard deviations below what the claimed mean was. Okay, now we're ready to go into the calculator and find out the area under there, this p-value here. It's going to be the TCDF, cumulative density function, and again t. The lower bound, that's your negative 99999. Just use some really, really small number. The upper bound, 2.564. Okay, and then we're going to put the degrees of freedom. Okay, it's lower bound, upper bound, degrees of freedom. Okay, and the degrees of freedom, is, of course, is 1 less than the sample size. Okay, we don't need to put the mean in because we already kind of used the mean and the standard deviation and everything in order to get this number, this test statistic. So it's a little different than the normal CDF calculator stepwise. Okay, so let's do that. Okay, so we're going to go under distribution, so second distribution. We want the TCDF. Okay, looks like number 6 there. Okay, TCDF, we're going from a negative, let's get some, we'll do it at the bottom, negative 9999. Let me just make sure we get this right, negative 2.564. Negative 2.564. And again, we had 11 degrees of freedom. Okay, this will find us the area, and we see it's about a 0.013. Okay, 0.013. That is our p-value. Okay, that's the area that we had shaded in purple up here. Okay, it's basically, if we ever need to interpret that, it's how likely is it to get the sample you got or further away from the mean or more extreme. Okay, it's about a 1.3% chance of that happening if the mean is 50 like they said it was. Okay, so we need to make our decision. Okay, this problem did not give us some significance level to use. Okay, so what you can do, the most common one when they don't give you one, is we're going to assume, and make sure you write this out because we need to know what you're using. We're going to assume alpha equals 0.05. Okay, a lot of problems they'll give you one. Okay, this one they just happen to not. So we're going to say, all right, that's how small the probability needs to be to show significance. Okay, our probability was even less than that. Okay, so we got something that was very unlikely to happen. So here's your conclusion then. Since P is less than alpha, okay, the thing that happened based on our sample was very unlikely. Okay, since we got that, we will reject HO. Okay, because again, here's the whole thought process. All of this was based on the mean being 50. Okay, we did this entire process assuming that was true. We got a sample. Our sample mean was 47.92. Okay, getting a sample that low, that far away from the mean is so unlikely. I mean, there's a 1.3% chance. It's pretty unlikely if the mean was really 50. Okay, so small p-values, you reject HO. Okay, so our conclusion in context is there is evidence okay, again, go back to our claims. We rejected this guy. Boom. We said, nope, I don't believe it. Okay, I rejected HO. So there is evidence for this guy. There is evidence that the mean is less than 50. So there is evidence that the mean number of minutes of music per hour is less than 50. Okay, so based on this data with this significance level. Okay, now don't get too caught up in this, because sometimes, you know, it depends on what significance level they give you. They gave us 0.05, okay, or they didn't give us, we assume that. Some problems might say, what if alpha equals 0.01? Okay, that's saying they want even stronger evidence. They want you to have a less than 1% chance of getting what you got. If we use that alpha for our problem, our p-value is greater than that significance level. Okay, so if that was the alpha given as 0.01, then we would not reject, because our p-value is greater than that significance level. So it's kind of like this fine line, and you just have to, you know, determine how strict you need to be. Okay, but again, since they didn't give us anything, we use the common one of 0.05. But I wouldn't go and bet your life to this radio station that they're not, you know, I wouldn't say you could actually prove them liars, basically, because they could just say, what if you used alpha of 0.01? Okay, if they send it to their statistics department, you're trying to sue them and make some money or something funny like that. Okay, but that's kind of the process. That's the conclusion. And hopefully that helps organize some things.